Hello everyone, I am Pushpita Chanda. I am the TA for this session. Let us start the session. So, in the last class, I have discussed the group velocity, phase velocity, Q switching, plasmode locking, and all those things. So, I want to discuss now pulse compression with pulse compression with or shortening help of gratings, drums. So, with the help of prisms and gratings, pulse can be shortened, and at the same time, with the proper arrangement, the pulse can be stretched also. So, how the pulse get stretched or uh, shortened by the pulse, by the prism or grating? That it's because of the dispersion. I will discuss the thing. Uh, okay. Here, dispersion is very important phenomena. GVD, that is group velocity dispersion. So there is called positive dispersion and negative dispersion. Sorry, it's group delay dispersion. So we know phase. Phase depends on frequency. So if we do Taylor series expansion of this phi, we get phi naught plus phi dash or first order of phi in of omega minus omega naught phi dash omega minus omega naught square by 2 factorial and so on. Right. So this is actually d phi by d omega. This is called first order dispersion. come phi dash dash. Okay. This is second order dispersion. Phi dash dash dash. That is third order dispersion. If phi dash not equal to 0, then the pulse got shifted in time. If phi double dash is not equal to 0, pulse got broadened. Okay, phi double dash 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 is not equal to 0. Both happened. It got shifted and broadened at the same time. So this is phi omega and this is omega. Gradient in second. So this is, suppose this is a pulse. It's a pulse. So when phi dash omega is equal to 0 and phi dash omega is equal to 0, transform, and this thing we go from frequency domain time domain. Pulse is centered around 0. Okay, but if phi dash is not equal to 0, the pulse kept shifted. Okay, it is 0. The pulse will become like this in time domain. phi double double dash is not equal to 0, then pulse will get stretched. Like but phi double dash is a derivative of phi dash. When phi dash becomes 0, phi double double dash will always become 0. So it is not true. So a second order dispersion is there. There is always a first order dispersion with that. Okay. Peak will shift. Dispersion work. Now dispersion can phi is spectral phase. Okay. I want to discuss some phi by d omega, which is phi dash, is called some group delay. First order dispersion that I have mentioned already. Looking for a few things. In frequency domain, and delta t is pulse width in time domain. So there is a relation between these two. The product of this cannot be greater than k. It always be less than or equal to k. This is called transform equal to. Now k is a constant which shape of the pulse. Okay. So however the pulse got stretched or something else, this is practical with time domain. But I will mention that when phi double dash is not equal to 0, the pulse stretched. Okay. But this is delta W or delta nu. This is the T. Okay. So the multiplication of these two should satisfy this inequality. So there is a value k. This is called time bandwidth product. T is called time bandwidth. You know the relation between the circular frequency. Okay, so then the product delta nu into delta t, there is also constraint the product delta omega into delta t. Only there is a factor of 2 pi. That's it. This is called spectral width in frequency domain, and this is can be called spectral width in time domain or more called pulse width or pulse duration. So this value k is different for different shape. For Gaussian, this value is okay. Value is 0.441. For hyperbolic rectangle, k is equal to 0.315. For square wave, is equal to 0.886. For the square is like this. Single-sided exponential wave. Point 110. So the square wave, it is in time domain. Okay. So single-sided exponential wave is like this. Single-sided exponential. So again it is I, and this is T. And metric wave, which is almost like this. Exponential. It will be symmetric. For that, k is equal to 0.142. So spectral width in the frequency domain into or multiply by pulse width should not be less than some value. they will got dispersed because of the medium and also for the geometry. So in any material, natural material for dispersion. And generally positive dispersion. So why does this dispersion get happen? Because of phi dash, phi dash dash, and so on. Phi is so phi dash is basically d phi by d omega. That's mean phi, this phase gets changed with frequency. Right. Right. The question. Because phi can be written as 2 pi cm by lambda, and n is refractive index. N gets changed. Any natural medium. And why n gets changed in any material? Of nonlinear effect. Any medium, it's happened. Then as at any point x and time n0 plus n2 into I. I is intensity. I was discussing K medium. I mentioned that when did mod locking, that in material like this is the beam, here intensity is high. So when intensity is high, refractive index is high. So this portion get focused. So all is this because of nonlinear effect. So because of this nonlinear effect, refractive index depends on intensity of the pulse. Also, as n changes, phi changes. Frequency. Dispersion happens. So in any medium, that is input electric field, and E out, this is the output electric field. Okay. And it will be minus I phi omega E E. So phi, it depends on omega. As n depends on omega, phi also depends on omega, because phi is 2 pi c n by lambda. Phi omega can be seen, phi of omega. Here it is a function, and this is variable, or we can say this is a function of omega. Okay, it's not multiplication. So phi phase can be written as omega by c into L to L. So function of omega. I omega is equal to omega by c and omega into L. So phi dash omega, what will happen? Omega into n omega. I'm writing this n as a function of omega because so that you remember that n should also be when we take derivative of this with respect to omega, we need to consider this. So L by C n omega plus omega into dn d omega. Now we need to write this expression in terms of lambda. Okay, then it will become thing gets changed with respect to frequency, then you know that it's also changing with respect to lambda, because frequency and wavelength is correlated. Okay. Now it is phi dash omega. Phi dash dash omega, or this can be called as Tg, and this is Tg dash. Okay. This is d omega L by C omega Tn d omega plus n. And okay, so when we change from omega to lambda, E is equal to omega into lambda. Omega is equal to this nu. Okay, equal to 2 pi c by lambda. So d omega is equal to minus 2 pi c lambda square d lambda. So you need to put that. Let me show you the calculation real quick. then put in this thing, it became lambda cube L by c square into d square n lambda square. So you may ask that here I am writing phi, phi depends on n and n depends on I, intensity. But I'm saying that in frequency, like phi changes with frequency. So n should be dependent on frequency. But I am writing that n is dependent on I. So this intensity part that changes with frequency. So I'll show in next class that calculation of this, how that intensity depends on the frequency because of a nonlinear effect. Now, pi double dash triple dash omega. Okay, this is Tg d omega square, which is a cube by c n d omega square plus omega d cube, and in lambda term, this is for any dispersive media. Now we see dispersion due to the arrangement of prism. So transparent media always give positive group delay dispersion. So we need negative group delay dispersion to compensate that. So how can we achieve negative group delay dispersion? By arranging the prism or grating. Okay. For prism group delay dispersion, or GDD, is equal to, first I want to like write Just write phi p phase because of prism, that is omega by c into n to L. So this is omega by c into, we can write optical path length. D omega lambda cube by 2 pi c square d square p optical by d lambda square. When we write it of lambda d square pi by phi p become minus 4 lp lambda cube by pi c square dn by d lambda whole square. Optical can be written as L into cos alpha. Alpha is the angle of prism. And cos alpha pi by d omega square is written as d alpha d omega at omega naught whole square. That we can write square. corresponding third order given by 4 pi square c cube dn d lambda dn d lambda plus lambda d square n by d lambda square. Okay. So what happened? Say it is a prism. So light passes through that, so it gets dispersed. Side and this side should be parallel. There is another prism which become the light parallel. This prism can be moved up and down. Now, sharp adjustment or dispersion adjustment, we need to like there is a ray, the ray got diverged. Now, to get that adjustment, for prism arrangement. With the same height. So if you move the prism upward, we get downward. If move this toward this, we get upward parts. So in case of prism arrangement, this through prism. So there is material plus dispersion prism arrangement. Okay. One thing I forget. Alpha. What is alpha? Alpha is angle of rays to central frequency omega naught. And LP is side of prism. So here we are called term total GDD. GDD is square d square n d lambda square is because of medium, and this is minus 4 LP lambda cube pi c square into dn d lambda whole square. This is because of PV management.
Hello.
Hello.
Uh,
Yes, yes, yes. I'm sharing.
yeah, actually, yeah,
Yeah. It's okay?
actually, yeah. So I did not attend all the previous problem solving session due to some work. So
They
can
are
I get those slides up?
there the slides and also the classes are there when let me tell you where you can get those things. Okay, just just a minute. Right, can you see my screen?
Yeah,
Yeah.
I guess.
Okay, when you log in the Swan portal, you see this thing, right? There is a option problem solving session. Okay, then you need to click here, then click here.
Okay.
Okay, here you get all the link. Okay, there is two TA, another one is another person is Vaskar. So all the YouTube link and presentation folder, and after that you will get my all session and the presentation folder link. You will get all those things in that thing, in that folder. Okay. Okay.
I don't think
The announce that will be mentioned in the announcement. Okay. It generally it should be in like MCQ, but if there is any difference in the pattern, it should be mentioned in the announcement. Yes, yes, will be there. But more weightage will be on the slides given by the professor. Okay.
yeah.
Uh, yeah. What I am teaching, it's like more of a extension. How this came, how Prism. Yes, this is the kind of extension ki how this thing happens, what is because of nonlinear effect, how dispersion gets affected, and the how we can like with the help of this dispersion effect we can create shorten the pulse. Th- that's I'm discussing all that thing. But just give for exam purpose, just focus on what like if you just focus on what professor have taught, that I think that should be enough. And some problems I have like discussed regarding coherence length and something that you should undergo, like in session third or seventh and eighth. The check at the slides, you can see the like questions that you should undergo. Okay.
Okay. Okay. So I'm ending this session.
Yeah, yeah, yeah.
Thank you so much.
Thank you. The third of the dispersion is 6 LP lambda 4 pi square C cube dn by d lambda plus lambda d squared n by d lambda square into d n d lambda minus lambda 4 by c 4 pi square c cube 3 d squared n d lambda square plus lambda d cube n d lambda cube. And this is because of prism arrangement, and this is because of material. Okay, now I'm going to move towards creating arrangement. Dispersion due to weighting arrangements. Okay. So, one thing I want to mention, what is the difference between prism arrangement and creating arrangement in terms of blue light and red light dispersion. So, in prism, refractive index of blue light is greater than refractive index of red light. So that's why velocity of blue light is less than velocity of red light. And the angle of deviation Blue angle deviated, blue light deviated much more than red light. But in creating arrangement, theta b is less than theta r, and velocity of wave is greater than velocity of wave. Okay, so please understand, like if this is a grating, and another grating is here. Okay, when light falls on, the blue light and red light get separated. Okay, this is blue, this is red. The light does not enter inside the grating. So, in grating, only dispersion occurs. Due to grating arrangements. For going into the calculation, some parameters of the grating should be known. So this is the angle. This is the normal at the angle of incidence. Is angle of incidence. Theta lambda is angle of reflection. Inverse is grating constant. Another thing LG. Okay. LG is grating distance. and this is the central wavelength. This is called N naught. So N naught is path traveled by central wavelength. So in this grating arrangement, the red spectral components travel a longer optical path compared to blue spectral component. Okay, so difference relation between L naught and LG minus lambda by d minus sine gamma whole square. Some people use N naught, some people use LG. And also we need to consider the grating equation which is sine gamma plus sine theta equal to lambda by g. Okay, this is constant for a given incident ray. Theta changes depending on the wavelength. Okay. Now, phi omega is spectral phase is equal to omega by c into T interval, which is omega by c into T path, optical path. KL is optical path. So GDD for prism, grating arrangement d square L naught of theta by lambda theta not by lambda. Theta function of lambda whole square and cos of it. And third order dispersion cube is equal to lambda by 2 pi c 1 plus lambda by d tan theta lambda by lambda. Typically 1 by d is of the order of 1200 lines 5 millimeter and gamma is of the order 28.6 millimeter. This is the grating angle. In the imaging, it is 28.6 degree and lambda naught if gamma is equal to 28.6 degree and lambda naught is 800 nanometer, then group pillar dispersion is of the order of 10 to the power 6 femtosecond square. In grating, we don't need to account well so here I want to mention another thing. Like, let us suppose, okay, due to 5 dash dash changes. I have mentioned that already. Or can say pulse pulse width delta in and output electric field has pulse delta out delta T in less than delta T out. Okay. Not because anything or some other thing, because of the second derivative of phase with respect to omega in the material or non-linear effect. What is the relation between delta T in and delta T out? Delta T, okay, then first of all, we need to know the uh, what is the form of the electric field. If electric field in omega is written like this, pi I naught, pi e to the power minus I pi. Okay, delta T out is basically delta T in square plus 4 and then 2 phi dash dash by delta T in whole square. Okay, that's how pulse width changes, and delta T out is change in the pulse width, not change in the pulse width, the output pulse width. Understand how much change is there. And all this is in femtosecond. In femtosecond. And when phi dash dash is equal to 100 femtosecond square. So the group delay dispersion is in the unit of femtosecond square. But phi delta T is in femtosecond. If 200 femtosecond square, 500 femtosecond square, 1000 femtosecond square, 2000 femtosecond square. Okay. So If delta T is 5 femtosecond and 5 dash dash, or GDD is 100 femtosecond square, then the output will be 55.7 femtosecond. It will be 1100 femtosecond. With 500 femtosecond square is GDT, we can put it will be 277.3 femtosecond. Second. 1109 femtosecond. See, when the T in was 5 femtosecond pulse width and it becomes 1000 femtosecond if there is a grouping dispersion. For 10 femtosecond, these numbers are 29.5, 56.3, 139, 277.4, and 554.6. The 5 femtosecond becomes 1109, which is almost 100 times. And this is 10 femtosecond when it is when 5 dash dash is 2000 femtosecond square, it becomes 550 femtosecond, which is 55 times. For 20 femtosecond, the same thing is 34.2, 72.1, 140.1, 278. For 40 femtosecond, this number is 40.6, 42.3, 52.9. This is almost 14 times. This is 80. This is 144.3. This is almost 3.6 times. So the group data dispersion, so you can see, is same, but 5 femtosecond pulse becomes so large, but 40 femtosecond pulse becomes large, but not that large. Per second. femtosecond is in is almost 1.32 times for 160 femtosecond. Almost same. So you can see that if delta T in is large, then group delay dispersion affects the delta T in very small in number. For 80 femtosecond, you can still, if there is a group delay dispersion of 500 femtosecond square, it is almost same. But even 100 femtosecond square group delay dispersion is very much enough, more than enough to destroy a 5 femtosecond pulse with uh, pulse. Conclude, the bigger the delta T in, less the effect. Laboratory, that's why GDB delta T in, we work with delta T in around 80 femtosecond. Because 160 femtosecond is still a very large bandwidth. It cannot like in ultra short physics, 160 femtosecond in terms of ultra short physics is very broad pulse. So usually 80 femtosecond pulse is being used. The question is, oh, question have two part. If optical path length traveled by an input ultra short pulse with central wavelength 800 nanometer and FWHM duration delta T is equal to 10 femtosecond in the glass medium of the four prism is L equal to 8 millimeter. Then what will be the FDD introduced in the pulse by the compressor overall and question number 2 is for the input transform limited Gaussian pulse of a using duration delta T equal to 10 femtosecond. What will be the FWHM duration of the pulse output from the prism compressor? The given data is LP is equal to 50 centimeter. dn by d lambda for prism is given 2 into 10 to the power minus 2 micrometer inverse. D square and t lambda square is equal to 5 into 10 to the power minus 2 micrometer to the power minus 2. So, the very simple question. The question has said that prism compressor. So we need to take into account the material dispersion as well So GDT for material will be lambda cubed by L. It's always good to remember the GDT for material cannot be negative. The negative GDT comes from the arrangement of prism or the grating. 2 pi c square d square and d lambda square. Putting all the value in micrometer. Okay. 2 pi into 3 into 10 to the power 8 into 10 to the power 6 whole square into 5 into 10 to the power minus 2. That is V26 prism is minus 4 LP lambda cube by pi c square dn by d lambda whole square. So it will be minus 4 to LP is 50 into 10 to the power 4 into 0.8 whole cube into 3 into 10 to the power 8 into 10 to the power 6 whole square to minus 2 into 10 to the power minus 2 whole square. And this AU for minus 1448 into 66 femtosecond square. So total GDT will be minus 1448 plus 362.16 femtosecond square will be minus 1086.50 femtosecond square. Now question number 2. What will be the T out? Square by 4 ln 2 5 dash dash by delta T in whole square. Putting all these value, which is 10 whole square plus 4 ln 2 into minus 1086 into 50 by 10 whole square. So it will become 301.4087 femtosecond. So from that, you can see from the chart that what will happen when 10 femtosecond is subject to 1000 femtosecond square GDT, where it was 1100. So it is almost in the same range. So this is the correct answer. Okay. So that is for today. The last class is tomorrow, and I will wrap this up. Thank you.